Hello, everybody. This is Sunday. It's April 17th, and we are moving into the final module of our online astronomy course, Module 14. And before I talk about that, I'll remind you that after we do Module 14 this coming week, the week after that will be the week of your final exam, week of your constellation quiz, and the week when your signature assignment is due. Now, all of those are already open. You can take those at any time. And so you can finish up the course whenever you would like to. Please don't forget the signature assignment. It's worth half a letter grade. It's just writing a short answer to a simple question, which is how does an astronomer think about astronomy? So write up an answer to that, submit it, and your signature assignment's done. So the final exam, remember, is not cumulative. It's just over this most recent material, just over modules 12, 13, and 14. 35 multiple choice questions. Like always, you can take it twice. The constellation quiz, I've sent out an email explaining how that works. You can take that twice if you want. The constellation quiz is closed book, whereas the final exam is open book. So please take a look at that email, and that'll tell you some more details about the constellation quiz. Okay, Module 14. Here we are at the end of the course, and now we're talking about the biggest subject in astronomy, which is the entire universe. And the entire universe, the study of the entire universe, is called cosmology. And as we saw last time, the universe is expanding. All of the galaxies in the universe are moving away from all the other galaxies in the universe, except the very closest galaxies. I mean, we're attracted to the galaxies in our own local group of about 40 galaxies. You know, those galaxies are held together by their mutual gravity. But apart from that, everything else is moving away from everything else. So the entire universe is expanding, and it's a special sort of expansion. Remember that objects that are twice as far away are moving away twice as fast. A galaxy that's 3 times as far away is moving away 3 times as fast. So you can imagine you're just, making a video of this, and then imagine that you run the video backwards. So now everything is moving in instead of moving out. And not only that, things that are twice as far away are coming in twice as fast. Things are moving 3 times as fast. I'm sorry, things that are 3 times as far away are coming in 3 times as fast. And that means that everything will come together at the same time. So that means in the distant past, everything was in the same place at the same time. There was nowhere else, because this was all of space being pulled together, as well as all of the matter within space. And that happened about 13.8 billion years ago. And since then, the universe all of a sudden started expanding. It was very hot, extremely dense, extremely hot, and it started expanding. And that expansion is still going on. And that expansion from a hot, dense beginning is called the Big Bang. And you can see the Big Bang is just an observation that comes from running the expansion of the universe backwards. That's all it is. And that is how the universe started out. Now, I want to say, and I'll talk about this a little bit more later, that we can't follow this backwards, running the video backwards, all the way back to time 0. And I'll explain more about why that is a little bit later. But we can start very soon after time 0. And that is when the Big Bang is. Okay, so, if the universe did start out very hot, very dense, there should be some sign of that in today's universe. Just like, if there was once a campfire glowing somewhere, burning somewhere, you might expect that if you come upon it a couple hours later, that it might still be warm. It might still get some warmth from it. And so there should be some warmth left over from this Big Bang, and there is. And we've seen it. It's all around us. It's called the cosmic microwave background. Microwave because it is black body radiation, and that black body radiation emits most of its energy at microwave wavelengths. It comes from every direction in the sky. And remember, black body radiation depends upon the temperature of the black body. And the black body radiation that fills the universe, the cosmic microwave background, has a temperature of 2.725 degrees above absolute zero, 2.725 degrees Kelvin. And we've actually measured it to that accuracy. So this is an amazing thing that we can still see this afterglow of the Big Bang. And you might wonder, what's going to happen in the future? Will the universe just keep on expanding? Will all the galaxies just keep moving away from each other until all the stars run out of fuel and there's a cold, dead universe of just white dwarfs and black holes? Or will somehow will the expansion stop and reverse itself? Well, astronomers wanted to know the question to that. And so they tried to make measurements of how the expansion of the universe was changing through time. And they had what they called a deceleration parameter they were trying to measure that would talk about how the universe was slowing down as all the gravity tried to pull everything back together again. And this was in the sometime in the 1990s. There were two groups of scientists, two different locations, making independent measurements of this. And they both came to the same conclusion, which amazed them so much they just couldn't believe it. But finally, they announced it at about the same time. They found out that the expansion of the universe is actually speeding up. It's accelerating. So instead of slowing down, the expansion is speeding up. And what can cause that? Well, it turns out that in Einstein's ideas about how gravity works, called his special theory of relativity, his general theory of relativity, it turns out that there's a constant in there that's called the cosmological constant. And it describes how the expansion could be speeding up. And what's causing that? Well, it's some sort of energy, and we have no idea what it is. It is probably the biggest mystery in all of science today. What is the nature of dark energy? We simply don't know. Now, theoretically, we've tried to calculate it, but we get the wrong answer by a huge factor. It's wrong by over 100 orders of magnitude. So it's wrong by a factor of 1 with 100 zeros after it. So it's massively wrong. So we really don't understand dark energy at all, but the observations are what's important. The observations tell us that the expansion of the universe is speeding up. And not only that, we can measure by looking at the cosmic microwave background, by looking at the patterns in the cosmic microwave background. We've been able to tell what the universe is made of. And it turns out about 68.5% of everything that there is in the form of dark energy. Another 26.5% is in the form of dark matter. Now, both those terms have the word dark in them, but they really don't have anything to do with each other. Dark matter is simply matter that is not shining. So the word there dark matter means not shining matter. Dark energy means we're completely in the dark about what it is. But so about 26.5% of everything is dark matter. And that means that the stuff that we're made of, atoms, protons, neutrons, stuff like that, hydrogen and helium and carbon and nitrogen, all of that only makes up 4.5% of the universe. And so that's a great joke on astronomers here. We've been looking at the stars overhead and thinking we've been studying the universe, and we've just been looking at the pretty shiny bits. The things that dominate the universe, we have yet to learn about. So I think that's really, really, really pretty amazing. And people also wondered, well, what is the shape of the universe? You might wonder, what does that even mean, the shape of the universe? Well, the way to think about it is that suppose I had two laser pens, two laser lights, and I just shot them out into space, parallel to each other. Now you can imagine that as those laser beams went out through space, they might come together, they might cross each other and meet at some point. In that case, we would say the universe has a positive curvature. And that's like if I draw two lines on the surface of a globe. If I were to draw a couple lines on the surface of a globe going up from the equator, then those two lines might start out going straight up, but they would meet at the pole. And so that would be a universe with positive curvature. Now, those two laser beams could keep going straight and never meet. And that would be a flat universe. And that's the sort of universe that exists on just an ordinary piece of paper, just right here. If I were to draw a triangle on that piece of paper, and I will, there we go, just draw a triangle. Well, that's a lousy triangle, but you can still see there's a triangle there. And that triangle has 180 degrees on it. So just good old math works, geometry works, like it works as if you were drawing on a piece of paper. That's a flat universe. Now, there's a third option, and that is those two laser beams shooting into space could slowly get further and further and further apart. And that's negative curvature. And if you think about a saddle that you put on a horse, and you start with your fingers just going to move along the saddle, and they start in the middle of the saddle and they go out toward the edge, and they just follow the surface, your fingers would move apart. And that's called a negative curvature. And so which one describes our universe? Well, we've been able to measure that too by looking at patterns of the cosmic microwave background. The cosmic microwave background isn't completely smooth. There are some spots that are a little bit hot, some spots that are a little bit cool. And by a little bit, I mean by about 1 part in every 100,000. So it would be out in the 5th decimal place that you'd see a temperature change away from this 2.725 degrees. But still there's a pattern there. And by looking at how big the spots of those patterns are, how big those spots are, you can tell whether the universe has a positive curvature, is flat, or a negative curvature. And in fact, you'll do this for yourself on your homework. So the story of cosmology is an amazing, amazing story. And there's more to tell too, because how far back can we go in time? How far can we go back and recreate the early universe with experiments here on Earth? Well, we can go back to the universe was about 1/1,000,000th of a second old. And that we can do that in our particles colliders. What happens is that they send a stream of particles in, those particles collide, they heat up, and they recreate the very early universe. And we can get back to about 10 to the -6 seconds. But we can't go all the way back to t = 0, as I said. How close can we get? Well, we can get back to a time called the Planck time, named after Max Planck, and that's 10 to the minus 43 seconds. And at earlier times than that, our physical theories simply fall apart. Space doesn't have its usual characteristics. Space is connected by a number of wormholes, and it's not continuous, and time doesn't have its usual meaning. So our theories can't follow that back to the very beginning. But still, you learn about the history of the universe. We can follow it forward. We understand it, we think, at least after 10 to the minus 43 seconds, which is pretty close to the beginning. And we can recreate it on Earth after a millionth of a second. So one of the big things that happened in the early universe was the creation of the atoms that we have in the universe, at least the lighter atoms. And that is called nucleosynthesis, synthesizing the nuclei of the early atoms. And that happened when the universe was about, 3 minutes old. And that's when protons and neutrons, which were just loose in the cosmos, were finally able to come together to form helium atoms, or helium nuclei, I should say, and some other, a few other light nuclei. And then the universe just evolved on from there. It's an amazing, amazing story. And there's a really cool simulation. If you'd like to see, well, what did that look like? All of the stars and galaxies forming, condensing in from nothing. There's been a massive computer simulation called the Millennium Simulation. And there's a link to those on the module, in the module links. Finally, and what this is behind me, is the Castillo, the major pyramid that's in Chichen Itza, the Mayan ruins that are in the Yucatan Peninsula in Mexico. And I was there a number of years ago, and we had strolled around the grounds and climbed the pyramid, during the day. And then at night, I wanted to go outside and look at the sky, and it was really beautiful. And we walked over to Chichen Itza itself, and the gate was open. So we just went on in. And what we saw, and I'll just show you here, what we saw was Orion just suspended above this Great Pyramid. And if you don't recognize Orion, that's because what's happening here is that it's on its side. So, Orion, you usually see it straight up, but here it's on its side. And oh my gosh, it was just so, so impressive. I tried to take a photo of it. It didn't come out. All I could see was the stars. You couldn't see the pyramid at all because it was absolutely dark. It didn't have the sky glow on the clouds that you see in this picture. I found this picture later on the web. But this is as close as I found to what I saw, just Orion just hanging there over the Castillo in Chichen Itza. I got to wondering about the people, the Mayans who were back 1,600 years ago, just looking up at the sky. And you have to wonder, what other people on other planets around around other stars, what other people who call another star their sun? Are there people like that? Is there intelligent life in the universe? Well, with all of the planets we know about, and we now think that on average, there's at least one planet for every star in the universe. And there's hundreds of billions of galaxies, and each of those has hundreds of billions of stars. And so there's a vast, vast number of planets out there. And it would appear that life on Earth took off like a shot as soon as Earth cooled. And so life arose very quickly. So I'm very willing to believe that life is common throughout the universe. Intelligent life, hard to say, because on Earth it took the freak accident with an asteroid hitting Earth to wipe out the dinosaurs so the little furry mammals could take center stage and evolve into we humans. So who knows if there's other intelligent life? I'd certainly like to think so, but we don't know for a fact yet. But we are searching for it. There is a search for extraterrestrial intelligence going on, SETI, Search for Extraterrestrial Intelligence. That's the SETI program, and you will also learn about that in this module. So that's the end of the course. And we've gone from just learning about how ancient people looked at the heavens, and here we are ending with how ancient people looked at the heavens, but those people may be around another planet, around another sun. There's still some cool stuff in the sky to see, and I will mention a couple of those. And so first of all, I'm going to pull up Stellarium. There we go. So here is Stellarium, and this shows Tuesday morning. This is the 18th. I'm sorry, Monday morning. This is the 18th. So this is Monday morning. And if you go out at about just before 6 o'clock, just before the sun rises, you'll see Saturn, Mars, Venus, and Jupiter all in a line, just like that. It's a great sight. And let me show you what's going on here. I'm going to just show you the ecliptic. And here is the ecliptic line. And remember, this is the plane on which the planets circle the sun. And so here's this plane, and Saturn, Mars, Venus, and Jupiter all lined up on that plane. That line is going straight toward the sun. So that's a great demonstration of the ecliptic plane. And if you go out to see that tomorrow or Monday, they'll still be there Tuesday. So there's Tuesday, Wednesday, Thursday, Friday, excuse me. So you can still see that on those other days. Now there's other stuff that's going to be happening as well. And that's going to be, let me show you that. That's going to be after the class ends, but I hope you're still going to be interested in astronomy after the class ends, because there is going to be very cool, a total eclipse of the moon. That's going to be happening on May 15th. And that's when the moon passes into Earth's shadow, and all of the sunrises and sunsets from all over across the globe hit the moon, and they turn it a blood red. This is a picture I took of a lunar eclipse several years ago, and it's really worth seeing. It's really cool. It really does look like that. And if you want more details about that, I have a link to a web page just under the link for this video. And here it is. I'll just pull it up. This talks about the eclipse you can see in Salt Lake City. This gives the date, May 15th, 2022. It's maximum at 10:11 p.m. And you can see here, this big circle is the central part of Earth's shadow, the deepest part. And here's the moon well inside that deepest part. So the moon's really going to be a beautiful red when this happens. And here's a timeline for when this happens. And you can see the maximum eclipse starts around, the maximum eclipse is at 10:11 p.m. The total eclipse begins at 9:29 and lasts till 10:53. So if you want to know any more details, you can go to this link to find out times for Salt Lake City, and any time in Utah, it's going to be about the same. And if you live someplace else, I'm sure you can go to this website and they'll have information for a location that's near you. So, hope you enjoy learning about cosmology. Hope you do well on the final exam and on the constellation quiz, and I'm sure the signature assignment will go well for you. And as usual, if you have any questions, you can always send me an email. I'll be happy to set up a Zoom meeting or meet in person in my office. And I hope you've had a good semester. I hope you've enjoyed learning about this incredible universe that we live in. I love telling people about it, and I hope you've enjoyed it. So here I'll say goodbye for the final time and wish you all well. So bye-bye.